Welcome back, ladies and gentlemen. We're moving on to 2.3 functions. Okay, we're going to be determining if a set of ordered pairs represents a function, and we're going to be using function notation. Now, function may be kind of a weird word to you, at least in the area of mathematics, so let's define the thing first. Okay, a function is a set of ordered pairs where each x value is paired with exactly one y value. Now, for example, if I've got -3 paired up with 2, and then 0 paired up with 7, and then 4 paired up with 6, and then 8 paired up with -1, I'm saying to you here that it represents a function since each x value is only paired with a single y value. Okay, now just to stress what I just did, okay, now notice -3, the x value of -3 is paired up with 2, and if I look, I don't see an x value of -3 anywhere else to be paired up with somebody else. Likewise, the x value of 0 is paired up with 7, but 0 isn't paired with anybody else. X value of 4 is paired up with 6, okay, and then the x value of 8 is paired up with -1. So none of those x values got paired up with anybody other than the person they were first paired with. So that's why it's good. Okay, but on the other hand, okay, if you notice I have the exact same 4 ordered pairs except for this guy right here. I changed the 8 into a 4. Okay, so now -3 is still paired with 2, and 0 is now paired with 7 still. 4 is paired with 6, but then wait a minute, 4 is paired with -1 now. So these guys do not represent a function since the x value of 4, as I just pointed out, is not paired with only one y value. It's paired with 6, and then it's paired with -1 again, and that's bad. We don't want that, so that guy would not be a function. Alright, so let's determine if each of these represents a function using those rules we just mentioned, or that one rule, I suppose. Alright, now the first one is 1's paired up with 3. And then if I look through my list, I don't see 1 paired up with anybody else, as the x value of 1 at least. And then 2, the x value of 2 is paired up with 4, and I don't see an x value of 2 anywhere else. 3 is paired up with 7, nowhere else. 9 with 15, 12 with 22, and then 18 with 40. So notice each x value is only paired with one other guy. So yes, he's a function. We like it, we love it, we want more of it. Alright, now the second example, okay, 6 is paired up with 2. And as I go down my list, I see 6 is paired up with 7. So hey, wait a minute, 6 went with 2, and then 6 went with 7. That's no good. We can't have that. That's bad. So this guy is big fat no. Not a function because of the 6 being paired up with both 2 and 7. Okay, moving down to this, now basically in a chart right here is basically just another representation of all those ordered pairs before. So here I've got 2 paired up with 9, and if I look down my list later, I see the 2's paired up with 0. So this guy, this 2 right here, he shouldn't be doing that, so that's no good. But if you notice, okay, 5 is also paired up with 2 different guys, with 8 and 3, and that's bad. So this guy's doubly bad. So a really, really big fat no there. Okay, moving around to this example here. Okay, this is supposed to be a separate example. Sorry about that. Okay, the x value of -2 is paired up with 7, and then -1 is paired up with 7. Now that might look like a bad thing, but remember, this is all about the x values. -2 is paired up with 7, and if I look down my list, there's no other -2 paired up with somebody else. Now there's a +2, but I don't care. That's 2 different numbers. Okay, likewise, -1's paired up with 7, which again is no big deal as long as -1 isn't paired up with somebody else. So this guy is a function, even though although 7 might make it look like it's a no, this is a yes. Remember, it's all about the x values. As long as each x value only has one y, the y's are irrelevant, as long as that x value doesn't show up again trying to get with a different y value. So you may have been thinking this, but what's the big deal? Well, mathematicians frequently like when there's a single response or an output to a problem based on the starting situation or input. Okay, now for purposes of mathematics here, the response, the output, is usually considered the y value, and the starting situation or the input is considered the x value. So here we go. The x, for most equations I kind of gave that away. The x value is the input, and then the y value is the output. Again, x is what we plug into the equation usually, and then the y is what we get as an output. So consider equations we've dealt with before. Let's go something simple. Y equals x plus 4, let's say. Okay, well, if I want my input, my x, to be 3, then what I do is say y equals 3 plus 4, and then I get y equals 7 out of the deal because 3 plus 4 is 7. So in this case, my input was 3 because that's what I plugged in as an x value, and then my output was 7 because that's what I got after plugging in the 3. Okay, so we have a function when the x value that we start with gives us exactly one answer. Kind of like what happened here. I plug in 3 and I only got 7 out of it. Well, most of the equations we've dealt with so far in the year have been functions. Okay, for instance, y equals x plus 7 is definitely one we dealt with before, or at least similar to ones we've dealt with before. And sometimes we graphed them, and we made an XY chart like this. So basically this is going to be an input-output chart. And if it helps you to think that way, there's your input, there's your output. Okay, so first of all, we have an input value of 0. So I plug a 0 into the equation, and 0 plus 7 gives me an output of 7. Notice I plugged in 0 and I only got 7 as an answer. I plug in 1, so my input is 1. I add 7 to that, and I get only the value of 8. Then I do it again with 2. 2 plus a 9, 2 plus the 7, got ahead of myself, gives me a 9 as an answer. That's a 7 right there, trust me. Alright, but again, notice that each x value I picked gives me exactly one answer, therefore it's a function. If I keep plugging in more x's, I'm still only going to get one answer each time. Well, naturally, we've got some equations that are functions, so the consequence is that there are equations that are not functions as well, or why bother talking about it? Well, however, these equations are generally messier. Okay, now I'm going to break a couple of rules, I suppose, a little bit here by having my y's in place first, and then we'll go back to the x's, if you will, but here we go. Hopefully it still proves the point without messing you up too badly here. Okay, so the y value I have is 2, and by my equation here, I have to square that y value to get over to my x. So 2 squared gives me a 4. Okay, and then if I move along with that, I get 1 squared. Well, 1 squared is 1. And then I get 0 squared. Now 0 squared is a 0. From here I get negative 1 squared, which is going to be a positive 1. And then finally I've got negative 2 squared, and negative 2 squared is 4. Okay, so again, I kind of broke a little bit of rules there. I kind of did an input-output almost a little bit backwards, but here we go. If I still think of my x's as my inputs and my y's as my outputs, notice that I've got a 4 here that gets me a 2, and then later on I have a 4 that gave me a negative 2. Likewise, I have a 1 that gave me a positive 1, and then I have 1 that gave me a negative 1. So I do get different numbers for y based on different, or having the same number for x. Okay, so basically some of the x values gave me 2 possible answers, and therefore this thing is not a function. Okay, basically if I tell you 4, you don't know whether to tell me 2 or negative 2, so that's kind of mean to do to you, so that's why it's not a function. It's not fun. Ha ha ha. Anyway, there you go. Okay, now function notation. Now, basically, functions are very important, so important, in fact, we came up with a special way of writing them. And here it is. Because functions are so important in mathematics, there's a special notation used when talking about equations that are functions. So instead of saying or writing the equation y equals x plus 7, we use the notation, well, I'm just going to write it first. We use an f with kind of a parentheses with an x inside of it. And then basically on the other side of the equal sign, we just leave it as is. Okay, so notice the x plus 7 is still x plus 7, but the y has been turned into this funny thing with an f and an x in it. Okay, now this thing is read as f of x. Okay, and it still equals x plus 7. Okay, so nothing fancy there, but that thing right there is pronounced f of x. Okay, I know it looks like f times x, but it is completely not a multiplication of f times x. It is just a way of saying f of x, and I'll get to why it is and what you do with it in a second here. But notice that the f of x, okay, again, this y right here just got replaced with this. So the f of x is just a fancy way to write the letter y. Okay, but it does have its purposes, and let's get to those now. Alright, so for using function notation, okay, it's basically a substitution notation, and it shows us, after we do our substitution, the x value or the input we use to get the y value or the output from it. Okay, for example here, if I've got f of x equals 3x plus 2, and I want to evaluate f of 5. Okay, now notice, instead of f of x, I've now written f of 5. So basically, this is the x value I'm going to use. I'll just say I'm using. Alright, so here we go. So now if I want f of 5, okay, now notice, instead of an x, now I've written a 5. And that's going to hold true on the other side of the equal sign. Everywhere I see an x, instead I'm going to put in a 5. So now instead of 3x, I'm going to write 3 times 5. And then basically just keep writing the rest of the equation, plus 2. Okay, now it's a question of using order of operations to work it out. So now f of 5, okay, 3 times 5 is 15, and then I bring down my plus 2, and so as kind of a final answer here, I get f of 5 equals 17. Okay, now I caution you against thinking of this as a multiplication. I said it once already, but I just want to reiterate it. This does not mean f times 5. So you're not going to try to divide by 5 here and get f by itself. This means f of 5. So here we go. From the final answer for this problem, it shows that we plugged in. Again, this is what I plugged in. F of 5 says that I plugged in 5 into the equation to get 17. Okay, and just to help reiterate the point, when I plugged in the 5, I plugged in an x to get the 17, which was the y value that I got. Okay, so furthermore, it shows the point on the graph of the equation should be, well, hey, look at this. The x is a 5 and the y is a 17. So if I'm talking about graphing an equation or something like that, that same notation tells me I've got the point 5 positive 17. Okay, I'll do a couple more here just to help drive the point home. Okay, if I've got f of x equals negative 2x plus 7, and I want to evaluate f of 3, okay, same thing again. Now f of 3, so instead of the x I've written a 3, so I just keep writing the equation, but anywhere I see an x, I put in a 3. Alright, and I just use order of operations right here. So f of 3 equals negative 2 times 3 is negative 6. Bring down my plus 7. So I've got f of 3 equals negative 6 plus 7 is positive 1. Okay, so again what this means is I plugged in a 3 for x, and I got a 1 for y. So it does show me both. So anytime I want to think about graphing, I can just plot the point 3, 1 right from there. Okay, now I've got g of x. So if you're thinking, hey, wait a minute, it's supposed to be an f. Well, the point of this one is it doesn't have to be an f. It could be a g, it could be an h, it should be a k, it could be any letter you want pretty much other than whatever letter you have inside the parentheses, because then that would be, quite honestly, just way confusing and crazy. So here it is. So if I want g of x and eventually g of negative 10, I have g of negative 10, and then again I just start writing my equation to 12 minus 7, and then hey, there's an x. So where there x is, I put in whatever x value is in the parentheses here. So now I've got g of negative 10, which again, hey, I had something and I plugged in a negative 10. So I've got 12, and I've got a negative 7 minus 10, so that's a positive 70. And so now g of negative 10. So when I plugged in negative 10, what I got out of there was an 82. Okay, that's all it is. Again, it just shows me what I plugged in for x and what I got for my y at the same time. Alright, now we got 4 try these. Here's the first 2, and as it says in the directions, just tell me if it's a function, yes or no. And here's the other 2 try these, which are very similar to the ones we just did. Alright, I'll see you in class.